think about it, that's the only way you can unambiguously define that plane if you have a single vector to work with. So it's a kind of convention in a sense, at least in this setting. Further on in physics, particularly when we get to second semester, it has some more physical relevance, but for now it's just a sort of labeling convention. So, I know there's a sort of couple of slightly confusing things just happened in the past 5 minutes, so let me recap what we said. First off, we're going to define torque, as our intuition has already led us to think, as being some sort of product of a force and a distance between where the force acts and the axis of rotation. It turns out that the relative direction of those two things is important. And so one way we can encapsulate those characteristics is to define the torque in either of these two ways. Okay? Same mathematical expression. The representation visually is different here, and again, I'm not going to try and convince you one is preferred over any other, it's the same. But I do find typically that half of you prefer one way of thinking about this, half the other. Is its magnitude. Fine, now we know its magnitude. Then we care a little bit about direction, and we can describe it in two ways, either clockwise versus counterclockwise from some reference point, or with a vector pointing in a direction that's perpendicular to the plane of rotation. And again, we're using the right-hand rule to define what that perpendicular direction is. So you're taking your right-hand fingers that kind of curving in the direction of rotation. Your single vector to define torque is defined by the direction of your thumb. Okay? So let me pause and ask you questions on that, because I usually find it's possibly confusing. Yeah?
Why is the, so like, yeah, I guess it's still don't fully understand why the torque factor, how that like visualized.
So visualize, and I don't actually think you mean visualize, I think you mean conceptualize, sort of. I mean, visualize, it's obvious, right? We're only allowed one vector to describe a plane and then a direction of rotation. So, first off, that vector has to be perpendicular to the plane. That's the only way we can unambiguously define a plane with one vector. So that's part of it, and then the second part of it is we need to somehow build in the direction of rotation in that plane. And so we have to make a choice. And yes, we happen to cook up this thing called the right-hand rule, which embodies that choice, which says if I'm rotating that way with my right hand relative to this axis, I'm going to call it a torque. It's positive coming out of the plane. And of course, if it's going the other way, the torque vector is into the plane of the chalkboard. So it's not intuitive in any sense that the actual physics is certainly not a force or something in this plane, right? So this is why I think it's just generally confusing. In electromagnetism, the use of vector product becomes more meaningful, but here it's simply a way of defining directions. It's not telling us that the torque, in the sense that you want to think of it as a force, because of course it embodies a force, it's not telling us that anything is happening in this direction. So you definitely have to get that kind of stuck in here. It's not telling you about the direction of the force as such. It's just telling you about a choice of convention that tells us the sense of the rotation.
So this defines that when we rotate basically?
Yeah, it defines not just the plane, but the direction. Yeah.
So theta is between the R and the force.
Yes. So defined by, this was just extrapolated up here, the direction between the R vector and the force vector. Yep. Okay, I know it seems straightforward. I pretty much can guarantee some of you will struggle with this a bit later on. That's fine, it's perfectly normal, don't worry about it. It's just a question of getting used to the definition. All right, so now we've got this idea of torque, and with that definition, it explains why, well, not yet, but it's about to explain why I do best by applying the force as far away from the axis of rotation as possible, and the orientation in which I apply that force. All right, so now we've got a definition of torque. You want to be careful with all of this. What about units? So, no big surprise, units are Newton meters, force times displacement, distance. We are very used to this point, based on our definition of work, in kind of introducing introducing a new unit for this, but actually we're not going to in this case. So work, if you remember, was the integral of force times displacement, so it has units, the same thing. And we tend to immediately talk about joules in terms of work done and energy and so on and so forth. But there's a kind of much more common prevalence to keep it as Newton meters, to kind of really stress that we are talking about a torque, okay? So even though it's the same units physically, we'll tend to keep it in Newton meters, all right? So hopefully that makes some helpful sense. It also embodies, sort of the idea that we could encapsulate it in this. So I don't know if you find that helpful or not, but it is the convention. Okay, so now we've introduced the idea of a torque acting on an object. As we can with forces, we can immediately start asking the question, what happens if we have multiple torques acting on a single object? So maybe I will come back, let me go here and have some logical progression in this. Superposition of torques. I'm going to illustrate this simply by a rather short and sweet example. So here we go. I have a rod which is pivoted at one end, and I am going to apply 3 forces to this rod. And with your help, I'm going to figure out what the total net torque acting on this object is. Okay, let me give you some information here. This is F1, this is F2, this is F3. I'll give you some magnitudes in just a moment. This is 15 centimeters. This is 5 centimeters. And in terms of the force magnitudes of F1, F2, F3, I will give you as follows. Okay, so let's just take a look at the setup. I'm going to work this on the chalkboard and I'll ask you to help me out directly. So I've got those 3 forces in red acting on that long, rigid rod. It's pivoted at this point. That's the axis of rotation. The axis is coming into and out of the plane of the chalkboard. So we want to figure out the net torque, and we're going to apply our definition here. Let's see if we can figure out what the net torque is. And I'm going to need to give you an angle here to be able to do this. Let me call this theta equals 30 degrees. All right, so how do we figure out the net torque? Let me come back up top here. So just as you're looking at that, ask yourself the immediate question, what direction does each of those forces individually tend to turn that rod? Okay, so let's quickly do that. This rod's pivoted about this point. That's its axis of rotation, into and out of the plane of the board. Force F1, how does that tend to affect this rod? Doesn't, right? Because the force is applied at a fixed point, a fixed axis of rotation. So that's not going to have any turning effect. It doesn't mean the force isn't there, but it's not going to have any turning effect. Right? So F1 is not going to contribute to the torque. We'll formalize that in a moment. F2, what directions are going to tend to make this thing turn? Clockwise. And this one? Okay. So in this case, we don't know until we plug in some numbers whether this thing overall is going to go clockwise or counterclockwise. So we need to figure it out. All right, so let's look at the torque from each of these. So the torque from force 1. So I'm going to write this as R perpendicular 1 times F1. My personal preference is usually to go this route. So I usually keep the force sort of untouched, so to speak, and then just figure out the perpendicular distance between the axis and the line of action. Okay, this one's easy because we've already determined that the line of action here is 0. So this would be 0 times whatever our first force was, 10 newtons. So this one's 0. The magnitude of the torque from the second force, so R perpendicular to F2. All right, what's R perpendicular to in this case? So my line of action of this force is vertical. What's the perpendicular distance to the line of action of the force for the second force? Yep, 15 centimeters. And the magnitude of this one, apparently 50 newtons. So this gives us 2.25 newton meters. Okay, I've done a quick conversion into meters along the way. Okay, so the question now is, how am I going to notate the direction? So one way I could do this is say that it's clockwise, or I could use my right-hand rule and ask the question, which direction does the torque vector point in this case? So which direction does the torque vector point in this case? Into the plane, right? So the convention, which I don't think I mentioned, but is if we've got clockwise rotations with that choice, we might put this also as a minus sign. Okay? So there are a number of ways I can say this. I can say minus, which corresponds to clockwise, or into the plane. All of these things are acceptable so long as you're clear about what you're doing. Okay? Again, this is a convention, so you just need to be clear about what convention you're adopting. So any of these are fine. Okay? What about the third one? Right, so this one's the only one that's going to be slightly interesting in that the line of action of the force is not perpendicular to this. So what would I put in this case? Say that again. Y cosine. So there are a couple of ways to do this. Again, look over here, and again, which way you prefer to visualize this is up to you. But let me take, in fact, this one to begin with. What I can do here is say, is the vector that's connecting the axis of rotation the point at which the force is applied. So that would be R and the upper of those two. And then what I need in that case is to look at the component of the force that's tangent to that vector. So I would in fact be resolving to get that component of F if I take the first root here. So in terms of the parameters shown here, what is that component given in terms of F3 and theta? Sine, right? So in this case, we in fact have, okay, I need to worry a little bit about what R is. I've done this the other way around, but what is R in this case? What's the distance between the axis and the point of application? It's 20 centimeters, right? So I need 20 centimeters in here. I need the magnitude of the force, which was apparently 12 newtons. And somewhere in here, I need an angle. So, you know, I could, if I'd done it in a formal definition way, of it being the angle between the R vector and the F vector, I could say it's the sine of this angle. But of course, just by looking at the symmetry of the sine function, the sine of this angle and the sine of this angle are the same, right? Sine of theta and sine of 180 minus theta are the same. So formally speaking, in fact, what I really care about is the angle between the r vector and the f vector. So again, there are various ways you can think about this. I'm not going to encourage you one way or the other. What I would probably put here is, if I was doing it that way, I'd probably put sine of 150 degrees. And this turns out to be plus 1.2 Newton meters. Okay, plus. So this means it is counterclockwise, or our torque vector is out of the plane of the board. Whichever way you want to specify this is up to you. Just make sure you're specifying it. Okay, so what does this tell you overall in terms of the net torque? What's the net torque, or at least qualitatively what's happening? Yeah. A little louder.
It's the sum of the torque, so it's just going to be 1.2 minus.
Right. So this minus this, I don't know exactly numerically what it is. It's clearly negative something, right? So which direction overall is this thing to? Yep. Okay. So now that's a simple example of superposition of torques. You're going to have quite a few problems that deal with those types of superpositions. Questions on that sort of fairly introductory worked example? Yeah.
So why
So, okay, so really, if I'm using my vector product definition, I care about the included angle between the r vector and the f vector. So when I do the vector product definition, that's the angle I care about. And so, okay, when you're actually doing this, again, you know that the sine of this angle is the same as the sine of this angle, just because they add up to 180 degrees. So it depends how you want to do it. If you're doing it with the formal vector product, you definitely care about this angle. When you're visualizing this, again, what I care about is the transverse component of the force relative to this. I can either use sine of this angle or sine of this angle. It's probably a little bit less intuitive for you to use this one, but it's perfectly okay, again, because of the symmetry of the sine function when it comes to 180 degrees. The last method that you could use, which is the one I tend to do, is stick with the line of action of the force and then figure out what the perpendicular distance RT is to that line of action. And yes, in this case, you know, again, it would be more intuitive, obviously, to describe this as r sine theta, okay? So either of them is okay, it just depends on which way you're preferring to determine this. And what I wanted to really get across with this is to show you that they're the same, but you might be inclined when you look visually at a problem to approach it one way or the other, or you might simply be inclined to go with the thing that I erased, which is the formal definition of the vector product, which is, in this case, r cross f. And in the formal definition of the vector product, you always care about the included angle between your first vector and the second vector. So I know they're kind of slightly different ways of presenting the same result, and I know it's going to be moderately confusing as you first work with this for some of you. That's fine. Just kind of work a couple of problems and just see which way comes more naturally to you, and then hopefully you'll be comfortable with it. Yeah.
Me?
Yeah.
Okay. So I have a question about the units. So you briefly said like it has the same units as like work, Newton meters, but we're going to emphasize that it's a torque. Is it like different because it's a cross product and not a dot product? Or like is it energy or no?
Unit-wise, there's no difference, of course. You know, physics doesn't know about the context of units. So the units are the same. Yeah, direction is important, which is not true for work, which is a truly scalar quantity. So, I mean, you can think of it that way. I just think of it as simply reminding us that it is somehow a product of a force and a distance. And for me, it's a much more immediate manifestation of that product than work. So that's as good as I can describe it as.
Is it like a form of energy then? Like, could you say it's also joules or no?
No, no, you can't. Even though it has the same units, it is not a form of energy. No.
Okay.
So, okay, asked that way, I better understand the question. Can I give you another quick example of something that has the same nominal units but actually encapsulates something quite different physically? Not off the top of my head, but there are countless examples, okay? We'll talk more about those as they show up. All right, so now we've got our idea of torque, superposition of torque. The next step is to go on to the rotational analog of Newton's second law. So, remind me what Newton's second law is for linear/translational motion. Okay? So net force is mass times acceleration. So, what's your guess as to what the rotational analog is going to look like? What's it going to look like? Yep. F equals mr alpha. Okay. So I like this fact that you're starting to, say, replace some variables by rotational analogs. But we kind of develop now the ingredients that give us really precise rotational analogs to F, M, and A in the linear scenario. Yeah.
Torque equals I alpha.
Okay. Yes. Okay, so there it is. Net torque, we apply to some object which has its own rotational inertia about some axis. So already there's something specific coming into the rotational inertia. And physically what we can actually say is it comes around somewhat the other way, which is to say that it's this. The resulting acceleration can be defined as the net torque divided by the rotational inertia. So this is the rotational analog of Newton's second law, okay? Now, it is also a vector equation. We've talked about the vector nature of rotational variables at this point, again, possibly slightly unintuitive. We're defining these vector directions now with our right-hand rule, and so those define indirectly the plane, the angular acceleration, and the plane in which our torques are acting. If you think about it, there's also some kind of implicit directional information in here. It's rotating about a particular axis, and we know that I depends on what that axis is. So this is more involved, it's more complicated, but nevertheless it's exactly analogous to the linear version that we've been working with for the past month. So, we're still only dealing with rigid objects, which for us, for the time being, means that I is going to be fixed in the problems that we're dealing with. So now we immediately come on to our sort of problem-solving strategy list, and it's going to look pretty similar to what we've seen before for linear dynamics. I'm going to work through this in just a moment, and then I'm going to work through a problem, a slightly more involved problem in class. Before doing so, I want to show you a demonstration which I think is a nice reflection of what we've just arrived at in terms of rotational second law. It has to do with these two setups up front, and I'm going to need a volunteer from the front row. Anyone want to come up? Okay, come on. Right, so most of you can see this, hopefully at least you can see the kind of important parts of it. So two setups that are on horizontal axles. So where are the axles here? These things in principle can rotate about those axles. So let's look at the shapes of them. So things that have sort of starburst, 6 rods sticking out of them. The rods in both cases are identical. And then there are 6 masses added to those 6 rods, but obviously the location of the rods is different than the two setups, okay? So halfway along from the center to the endpoint in this case, and then right at the endpoints in this case. So that's the shapes. Those are the objects in a sense that we're going to apply torques to and see how they respond. So the question next is how are we going to apply a torque to them, and ideally a fixed torque. This bit's a little bit harder for you to see, but on the back end of these axles are some sort of spindles, and then wrapped around them, just pull this up a little bit, is a string, and on the end of a string is a mass, and the same thing is on the back of that one. So what we're going to do in a moment, and if you can just grab that mass, keeping it looped through the string, and just, if you can stand on the other side, all together, yeah. And this is the tricky bit. What I'm going to ask you to do is take that and just drop the mass through the hole, keeping it still hooked into the loop of the string, and then just suspend it, okay? All right, so I'm going to wrap this thing up again. Just bring this all the way back up. So you can see the sort of motion that's happening here. And eventually this is going to come back up to close to the top. All right, so roughly comparable. Just hold on to that for a moment. All right, so let's quickly recap what we're going to do. And in a moment, we're going to let these things go, but not before you've predicted what's going to happen. So these spindles on the back, they have strings wrapped around them, and they have identical masses hanging from them. Can't see this very well, but those spindles have a diameter that's maybe 5 centimeters or so. And so if you think about what's happening back here, these strings are wrapped around that kind of little cylindrical object, and then the mass is hanging from one side of it, okay? So, once we let this thing go, there's a force acting on the mass, force of gravity, so the weight is acting downwards. It's equal in both cases. Equal force. They're wrapped around identical cylindrical spindles at a common distance away from the axis of rotation. So we've got common force in these two setups acting at a common offset perpendicular distance from the axis of rotation. What does that tell you about the torques acting in both of these setups? Same, right? So this is a setup that applies the fixed torque to two objects that have same mass, but different mass distributions. So they have different rotational inertias. Which one has the larger rotational inertia of these two setups on the front? One on the right. Why?
How local inertia is defined as times the distance squared,
Right.
and the mass at a point farther away.
Right. Good. So in fact, the masses are twice as far away from the axis of rotation for this one as they are for this one. It's a complicated shape, but we could calculate its overall rotational inertia using some of the tricks we've learned this week. We could maybe figure out where the center of masses of these masses themselves are based on symmetry, center of masses of the rods, so on and so forth. But roughly speaking, you would expect this one to have a rotational inertia that's about 4 times this one, maybe a little bit less if you think about the details of the mass distribution. Let's say it has a rotational inertia that's 4 times on the right compared to the one on the left. And we're exerting a common torque, net torque on both of them. What's your prediction about the resulting angular accelerations of these two objects when we let the masses go? Yeah.
The acceleration of the left one will be 4 times the acceleration of the right one.
Right. Okay, good. So let's see if your prediction is borne out. 3, 2, 1. So this one accelerates way faster than this one. Nice. These things are going to go back and forth for a while. It's kind of fun. But it's a nice encapsulation of this. It folds in what we've been learning this week about rotational inertias, and obviously torque and angular acceleration. For a fixed torque, this is inversely proportional to this. And so that's what we're seeing.
Friction?
that's interesting. Kind of surprising that it stopped so quickly. I don't know, something kept that one fixed in place. So yes, friction of some sort. I guess they need some oiling. All right, good. So now we know a little bit about rotational second law. Let's work through our problem-solving strategy, and then I think in the remaining minutes I'm actually going to work through a somewhat involved problem. All right, so here we go. Select a body to analyze.